Okay, these are the second half of the 5.2 Algebra 2 notes. So we're picking up right above example 5. We're talking about like radicals. So like radicals have the same index. And what that means is, like, for example, they are either both fourth roots, or they're both fifth roots, or they could be both to the 1/6 power. So they're the same, okay? And so if they are the same, then they're like radicals. And when they are like radicals, it's kind of like having like terms. You can add or subtract them. So right here, you see that we have a fourth root of square root of 10. I added the 1 right here, so that'd be 1 fourth root square root of 10 plus 7 fourth root square root of 10. So altogether, you have 8 fourth root square root of 10. And you just add them like that. Now right here, you see they are both 8 to the 1/5. So since they're both 8 to the 1/5, then you can go ahead and you can add them together. So you have 2 8 to the 1/5 plus 10 8 to the 1/5. That gives you 12 8 to the 1/5. So they not only have to have the same index or the same power, but they also have to have the same number, the same base. Okay, look at C. On C, they are both a cube root, but they're not the same number. You can't right now take the cube root of 54 minus the cube root of 2. They have to be like both cube root of 2's, for example. So what we're going to do is we're going to break down 54 using a factor tree like we had learned previously. So 54 is 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. Now remember, when it's a cube root, you circle 3 of the same number. So instead of partners, you circle groups of 3. So what that means is the cube root of 54 is the same as 3 cube root of 2. Remember that the numbers we circled are all the same. That comes outside. And the leftover numbers that we didn't circle go inside. All right, so now you have 3 cube root of 2 minus the cube root of 2. So 3 cube root of 2's minus 1 cube root of 2 leaves you with 2 cube roots of 2. And that's your answer. Okay, so on D, we are simplifying. So we're going to simplify the 64, and we're going to simplify the y to the 6th. So because it's a cube root, how we're going to break this down is we're going to start with, if we look at our sheet of powers, 64 is on that sheet. So I can just put cube root of 64. I don't have to do a factor tree because it is a perfect cube, so that saves me some time. Now, I can break up y to the 6th as the cube root of y cubed and the cube root of another y cubed. So remember that y cubed times y cubed does give you y to the 6th. If you recall, you add the exponents, so it's the same thing as a y to the 6th. I just broke it apart into y cubed and y cubed. The reason I did that is because the cube root of something cubed cancels out and just leaves you with y. And so the cube root of y cubed is just y. The other cube root of y cubed is just y. We can look at our cheat sheet for the cube root of 64. That's 4. So I end up with 4 times y times y. That is 4y squared. Okay, on example E, these are two things inside the fourth root. So remember that we learned that when it is a quotient, you can break it up into its own roots. So you can have the fourth root of x to the 4th on top, and on bottom you can have the fourth root of y to the 8th on bottom. Now, I recognize that y to the 8th is going to be able to be split apart nicely. So if you break y to the 8th up into y to the 4th and y to the 4th, that is still y to the 8th. So I split it up into y to the 4th and y to the 4th. Why I opted to do that and not something like y squared and y to the 6th is because I'm trying to get the fourth root to cancel out. And I have fourth root and a fourth power here. So on the denominator, that's going to give me y times y, which is just going to be y squared. Now on the top, I also have the fourth root of x to the 4th. which can cancel out and just be x. Now, I am going to add in one little detail here, which can kind of be hard to remember, but we're going to actually write it as the absolute value of x. And I know that's kind of crazy, but when you have to do it is when you have an even root of the same even power. So for example, like the sixth root of x to the sixth, you're going to write the absolute value because you're assuming positive. If you recall, we have the times where it can be plus minus. And so this is one of those special scenarios that when you have an even root of the same even power and you're simplifying the variable, you're always going to write it as an absolute value. You do not have to do anything if it's an odd root. That's not something you have to concern. So it's only the even root of the same even power. All right, so write each expression in simplest form. All right, notice this has a fifth root out here. So I'm going to break everything I can into multiples of 5. So the 4, if you look up on our paper, 4 doesn't really have any fifth root. So we're just going to write 4. A to the 8th, I'm going to break up. I'm going to have a to the 5th and a cubed. That still makes a to the 8. I just pulled off 5. So the reason I choose to pull off a to the 5th is because it's a fifth root. Now on b to the 14th, you want to pull off as many as possible. So I'm going to break that down into b to the 10th and b to the 4th. That still makes 14. The reason I chose 10 was because that's the largest amount of 5s that can go into 14. And then c to the 5th, that fifth power is already divisible by 5, so I'm just going to leave it as c to the 5th. Okay, so why we did this is because the powers that are divisible by 5, these can simplify more right here. Okay, so let me show you what I'm doing here. So if you have the fifth root of a to the 5th, that just gets you a. So that a is going to come out in front. If I have the fifth root of b to the 10th, that is the same as saying b to the 10 over 5. Remember, powers on top, roots on bottom. 10 over 5 is b squared. So b squared comes outside. And then same with the fifth root of c to the 5th, that gives you a c. Now everything I did not highlight is still in the fifth root. So I have inside the fifth root 4, a cubed, b to the 4th. And that's our solution. Okay, on example 7b, the whole problem right here is that I have a root in the denominator. Remember that that is not allowed. So I see here that it is a cube root. So the cube root tells me that I want the power to be divisible by 3. So what I'm going to do is I'm going to say, okay, I need whatever the denominator is, I'm going to move it up. So instead of y to the 8th, I would like it to be y to the 9th. Okay, you always increase the power. So it's to the 8th, and that's not divisible by 3. So if I could put another y on there and get y to the 9th, that is divisible by 3. So I think to myself, how can I get y to the 8th to turn into y to the 9th? I just need another y. So I multiply by the cube root of y. Now what I do on the denominator, I have to do up top on the numerator. So I also have to do the cube root of y. So on top, I just have x times cube root y. On the bottom, when I have the cube root of y to the 9th, rewrite that as a fraction. Remember, the power goes on top, the root goes on the bottom. So you get y to the 9 over 3. 9 over 3 is just 3. So you get y cubed. And that solves my issue of having a radical on the denominator. That's the part that wasn't allowed. So this is now rationalized, meaning there's no more radicals on the bottom. Okay, so on 7c, this is going to use our exponent properties. The first thing I'm going to do is this 14 over 2. Those are just numbers. They don't follow exponents. They just divide. So 14 divided by 2 is 7. I'm going to go ahead and rewrite the top x and then y to the 1/3. On the denominator, I have x to the 3/4. And let's go ahead and move this z to the -6. Remember that the negative will move it up. to the top. So it'll be z to the 6 on top. The one other tweak I'm going to make is this x on the top. I'm going to write x to the 1 just so it has a number there. Okay, so we have the 7. Now, when you have x to the 1 over x to the 3/4, remember when it's in a fraction, you subtract. So you do 1 minus 3/4, that gets you x to the 1/4. There's no other y's and no other z's to simplify, so you just write those down. And then the one thing you have to do, if you go back to the original problem, do you guys see that on the bottom there's an x and a z? So you could not have had a 0 down there. So we have to write down that x cannot be 0 and z cannot be 0. And that's because if you went to the original problem and if x or z had been 0, it would cause you to divide by 0, which is of course not allowed. There was not a y on the denominator. That's why I don't have to write that y cannot be equal to 0. Okay, this is kind of jumping back to some other things we learned today. So we have 5 square root of y plus 6 square root of y. They are the same root. They're both square roots, and they're the same number inside. They're both y's. That means they're like radicals and can be added. So if you have 5 square root y plus 6 square root y, you get 11 square root y. So we're going for the same concept over here on B, but the difference is right now they're both cube roots, but they're not the same thing inside. So currently I couldn't add them. So I'm going to try to simplify this cube root of 54z squared. So what I'm going to do, I see the other one has a z to the 5th, so I'll figure that out in a minute. But I'm going to start by breaking down the 54 as a factor tree. Sorry, that 3 should be right there. So if I break down 54 as a factor tree, it's 2 times 27. 27 is 3 times 9. 9 is 3 times 3. Now remember, because it's a cube root, you circle 3 of the same number. So this 3 comes outside, and then the 2 is left inside with the z squared. All right, so this turned into 3z cube root of 2z squared. The reason why this z came in is it was this z up here by the cube root. So when I simplified the 54, that 3 comes out in front with that z. Okay, now I also need to break down on this, the 2z to the 5th. So how I'm going to break that down, 2 is already broken down as much as possible. So I can't do much there, but I can break down the z to the 5th. I can rewrite it as z cubed times z squared. That's still z to the 5th. So that will give me, and then I guess there's still a 2 inside. So this z cubed, if I do the cube root of z cubed, it is z. And that comes outside, and then I still have 2z squared. So this right here, it had 12, and then z, and then cube root of 2z squared. All right, so now the cube roots both have 2z squared in them. So now you can do 12z minus 3z, which is 9z, and you have cube root 2z squared. And that's our solution.